Good morning, class. Welcome. This is Mr. Roberts, and you found yourself right here at a place where you're looking at some quilts. Maybe grandparents' quilts. I don't know. Over the next couple of days, we're going to be looking at what happens to polygons, well, actually even lines, points, when the Cartesian coordinate plane is subjected to some transformations. When a reflection, a rotation, or a translation occurs, what's the relationship between the shape we started with and the resulting image? What do these transformations do to everything on the plane when they get moved? For example, if we consider these particular polygons, some convex, some concave, but they can be transformed by rotation, and we can see that they exist in multiple spaces on the plane. So the first thing that I would like you to do today is, in the shared doc that I've distributed to each of you, there are a total of 8 objects where I ask you to subject the polygons to some sort of rotation. And this first one, for example, is a 180-degree rotation, and this means clockwise, the direction of the clock, so around this way. This one's counterclockwise, 180. Some are 90 degrees. Here's 270, here's 360. The dot indicates the center of rotation, so we're rotating about that particular point. Now, to help organize your work, what I've done is I've placed a link here that says rotation tool. And when you click it, you get this sketch that I put together in GeoGebra. For simplicity, I've eliminated a lot of the tools and left you just with 4 tools. One is a polygon tool, and basically what you do is click vertices of any polygon that you want. I'll go to here, and when you're done, you just do a final double click on the last one, and you now have a polygon, and you can now subject this to some rotations about this point C. So to do that, you'll click on the rotation tool, and then you click what you want to rotate it around. And if you want to use this slider, you're going to delete everything here and just type the letter R. So you can see this is going to go, I'll make it go clockwise first. So you need to pick counterclockwise or clockwise, but I'm going to make it go clockwise about point R, and then I just click OK. And now you can see I can take this and rotate it exactly there. Where is it at? There's 95. There's 90, 91. There's 90 degrees. So if I rotate this shape 90 degrees about point C, you can see I get this new shape that is now here. You get to a place where this is not what you want anymore. If you just refresh the browser, or if you click undo, you can take back steps for things that you'd like to get rid of and then begin again. So using this tool, you should be able to very easily visualize what happens with each of the shapes that I've shared with you, and see exactly what happens when you rotate the desired number of degrees about this point. And again, once you have the polygon, the procedure is click the rotation tool. We're going to say we're going to rotate this shape about this point, and then I would just say by R degrees if you want to see it happen. If you want to just go ahead and say, I'm just going to go 90 degrees, right? You see when I type 90 degrees, it does have the degree symbol there, which is important. R doesn't need the degree symbol because R is expressed in degrees. But I've got 90 degrees, and I can go clockwise or I can go counterclockwise. If I go clockwise, this shape goes exactly to that spot. And then I'm going to try this again. I think I can take this, right, and I think I could say I want to rotate this shape around this point by 90 degrees, and I want to go clockwise also. Yeah, and there it goes. So using this procedure, you should be able to look at all of the polygons that I've set up here and then just sketch the result. And I know you know what that looks like, right? If I wanted to sketch the result, you just use the segment tool and draw that shape. But also, if you want to, you could screenshot your images from GeoGebra. You could screenshot this and just paste it in there. And when you do the screenshots, it's better if you do the ones where you're just selecting part of the screen, not the entire screen. Yeah, that would work well because you could see both the original polygon and the result once you do the rotation. The next task is a little bit more obscure, and it's I think it's a little bit more complex as well. So I'm going to step us through a good chunk of this, and I just ask that you kind of follow along and then copy and paste your results into this area on the next slide. So we're going to read through this, process it, and we're going to paste our results here. There is another tool that I designed for this specific question. If you open that up, it looks like this. This, and you can see that there are more tools now, and also the Cartesian coordinate plane is here. So the tools that I have are the point tool. We would use this if we wanted to create points. If we want to draw segments, this is segment tool. Here's our polygon tool again. Rotation, what are you going to rotate, and what are you going to rotate it about, and how many degrees? It'll ask those 3 questions. This will allow me to just move the entire graphics view around, so I can just shift the whole view around at once if I need to. And then I have 2 measurement tools. This will let me measure the angles, and I'll talk about how to use that. And this will allow me to measure distance between 2 points on the Cartesian coordinate plane. And when I have you use this, I will try to pull out just the specific tools that you need for any given task. But I do ask that you try and invest in learning what these tools do and how to use them. Also remember, anytime you get to a place where you're not sure what happened, you can use the undo, and if you go back too far, you could redo and bring back some things that maybe you wanted to keep. So let's do a bit of reading here. So this is problem number 39. We're only doing 38, 39, and 40 today. And it says definition of rotation. So what exactly is a rotation? If a figure is rotated, how can you describe it? Investigate this question below. Okay, so if a figure is rotated, how can you describe it? On graph paper, graph the points A and B. A is going to be at 4, 1, and B will be at 2, 5. So let's go ahead and do that task first. So using my point tool, I'm going to go ahead and graph 2 points. They said one of them was A was at 4, 1, so X is 4, Y is 1, and I will click it. And if it's the only point that you've used so far, it will give you A. If you've plotted other points, if you go through and delete those points, so for example, if I hit delete tool, I can come over here and I can click this and it deletes that point. But you can see it will basically just relabel points just using the alphabet. But if a point A is already used somewhere, the point you get is certainly not going to be A. But with a clean sketch, if you go to 4, 1, click A, you'll have A. And then over at the second point is B, that's when X is 2 and Y is 5. So those are the 2 points that we're asked to graph, A and B. And then the instructions say, then using tracing paper to rotate the 2 points 90 degrees counterclockwise about point O. Okay, so point O, they label it in the book as the origin. I've labeled it C here because in my mind it's the center of rotation, but they're calling this point O. And then it says mark the 2 points A prime and B prime on your graph paper. So if I want to subject A and then B to a 90-degree rotation, what I'll do is go ahead and grab my rotation tool. I will click on A, and then I'll click on the center of rotation, and I will say that I want to rotate exactly 90 degrees. So I'll just delete this and type 90. You can see it's got the degree symbol up there. I'm going to go counterclockwise because it says to go counterclockwise, and I hit OK. So when I rotate 90 degrees, you can see, boop, that's where A landed, right there. Interesting, I can see here before the slope from 0 to A was up 1 over 4, positive 1/4, and now the slope is down 4 over 1. So I can see that these are indeed perpendicular to each other because their slopes are opposite reciprocals. Let's do the same thing for B. So I select point B, and I've already got the rotation tool on, so I select B, then I select the center of rotation, and then I just type in 90 degrees and make sure it's counterclockwise and hit OK. So there's B prime. So, and again, if I look at B, B had a slope of up 1, 2, 3, 4, 5 halves, 5 halves. This has a slope of down 2, right, negative 2 fifths. So this is a nice place to review the fact that if lines are perpendicular, their slopes are opposite and reciprocals. The next thing we're asked to do is draw some line segments that connect A to O, B to O, A prime to O, and B prime to O. Using tracing paper, compare the lengths of and angles formed by these line segments. Which lengths are equal? Which angle measures are equal? Be specific. To help, you may want to draw line segments connecting each point with O. That's funny because that's what they suggested that I do. So let's go do that. So using the segment tool, I can draw segments that connect O to A and O to A prime. And again, I just point out this up 1 over 4 and down 4 over 1. Those are clearly opposite reciprocals. So when I rotated this plane, we see that we got this 90-degree rotation here. Let's do the same thing for B. So from the center to B and from this center to B prime. Now to measure segment lengths, I can just click on the distance tool, and if I click on a segment, you can see this is 4.12, this is 5.39, this is 4.12, and this last one is 5.39. So I think the important thing to point out is that when I subject the Cartesian coordinate plane to this 90-degree counterclockwise rotation, it doesn't change the length of any segment, right? From C to A, or in the case of the textbook, from O to A and from O to A prime are both 4.12. Rotating 90 degrees didn't change the length. And same thing here, this was 5.39, didn't change the length. Measuring angles is something that it feels like it takes a little bit of practice, and I think the reason I may do this wrong the first time, but I think what happens is it kind of goes counterclockwise. So if you wanted to measure the angle from A to O to A prime, you would click this first and then it'll go counterclockwise and then measure to there. So let me try this. I'm going to click on this segment and then I'm going to go click on this segment, and that did it, right? So if I was to do it in the opposite direction, I'll just show you this. If I was to click A and then go clockwise to where I wanted it to land, you notice it didn't go clockwise. It went around the backside and measured it, and that's 270. So I can undo that. So again, if I want to measure the angle from B to O to B prime, I'm going to do the same thing. I'm going to click this and then just intentionally go, I click this one first because I see I would go counterclockwise to get that, and I just click it. And there, it put a 90 degrees there also. They're both difficult to see, but it is reassuring to see that, yeah, when you subject the Cartesian coordinate plane to this 90-degree rotation, this whole thing rotated 90 degrees as well. This next question, C says, predict the measure of angle AOA prime, verify its measure. Well, we did that, right? If you look closely, well, I don't know that. Well, I guess we kind of predicted because we were pointing out the slopes were opposite reciprocals. But yeah, when we did measure it, we thought because the slopes were opposite reciprocals, it would be 90 degrees. And it turns out, yeah, not only are those lines perpendicular because of the relationship of their slopes, but when we measure it with the angle measurement tool, we got 90 degrees also. D says, why does it make sense that for all points P on the graph, a rotation about point a point O moves it to a new point P prime, so that the distance from O to P is equal to the distance from O to P prime, and the measure of angle pop PO P prime equals the measure of the angle of rotation. Use tracing paper to make sense of this relationship. And while tracing paper is certainly a good suggestion, we're using GeoGebra, so I'm going to delete, and I'm being careful as I do this not to delete this tool and not to delete this. If for some reason I delete wrong things, all I have to do is refresh the browser and it will reload this page to its default state, which looks exactly like this. So I'm going to pick some other point. It doesn't matter which point it is, this one for example. And it doesn't really matter what happens if I go ahead and pick this segment from here to here. I'm just going to say, let's just do it for any arbitrary angle. So with my rotation tool, I'm going to rotate this line segment about this origin, and I'm going to do it by R degrees. So R degrees, and this time I'll go counterclockwise as well. So it says, hey, if I was to do this, right, no matter where I land here, even if it's a strange angle like 173 degrees, at the end when I measure the length of my original segment, O to A, or from the origin to A, and I measure the length of this segment, they're both 6.32, and you can see that I went 173 degrees. If I was to measure this angle from here going, I have to do it counterclockwise and then click this one, I can see that's 173 degrees also. So I think the point is that this rotation about the origin, right, is not stretching it out and moving it anywhere. It's just going so that it, back to the beginning. It's just going so that it's just rotating, and that how far an angle I rotate is going to equal exactly to the angle between the original and the image of that shape. And these are always going to be the same length because I'm not stretching them, I'm just rotating around the origin here. So somewhere in there, I think there's a response to D. So many of you are better at wording things than me. So think about it. Why does that make sense? Give me your take on why for D. And then finally for E, use tracing paper to help you explain why the rotation does not change any angles or lengths of a figure. When measures do not change, and this is interesting. E actually feels like if you've answered D, you've kind of hit this, but then they want to point something out. When measures do not change something, or when measures do not change, some mathematicians use the term preserved, as in the angle measures are preserved. So when we do these rotations, two things were preserved, right? Anytime we perform a rotation, not only are the distances preserved back to the origin, but also the angles are preserved as well. So when I talk about preserved, I'm not talking about canning peaches or strawberry preserves. I'm talking about the fact that the angle measures and the distance lengths are all preserved when polygons are subjected to rotations. Okay, so just a bit of housekeeping then. For question 39, my expectation is that you paste, and you can just completely hide this graph. You don't need to use this grid at all if you don't want to draw it. You can just copy your images from GeoGebra, paste them here. But as far as your answers to 39, I'd like for you to type them here for A, B, C, D, and E. If some of them involve just verifying that you did something, just say C graph. Some of them are going to require that you think and write a response as well. The last question we're doing today is question 40, and I've set it up here. And we're going to look at some of the text for 40, but basically same deal. You're going to be responding to things here. I don't think that you're going to need GeoGebra. This is an image that we've already talked about before. We've got triangle PQR, and triangle PQR is reflected about line L. And you're going to be asked to do several things with that information. So this is what 40 looks like from your text. You're going to need to look at this while you do 40. But we'll just look at it briefly here. So now that you know more about slopes of both parallel and perpendicular lines, we're going to revisit question 325 from earlier in this chapter. We have this diagram on our slide deck. You can see this quite large. It says find the diagram, right, which shows triangle PQR reflected across line L to form triangle P prime Q prime R prime. So this is what we started with. It's reflected across L, and this is what we get. Use your ruler, or in this case just the line tool in slides, to draw some dashed lines that connect P to P prime, Q to Q prime, and R to R prime. What is the relationship between these three dashed line segments? Use your knowledge of slope to algebraically verify your observation. So I am going to actually stop at this point. I'll just say, not this, I wanted to go back to, here we go. That I know that you know how to use the segment tool, and it says make them dashed lines. So if I was going to go from P to P prime, right, I could make it a dashed line by hitting this and just hitting the dash icon there. So there's a little dash line. So again, do everything that the prompt requires with the diagram, show that information here, and then type your responses for A. So again, today, 38, 39, and 40. Also, I want to point out that the assignment today, the review and preview, is the only review preview you'll have for the next 2 days. So the due date is not a mistake. It actually is due on Tuesday at 11:59. This is Ms. Roberts. Have a great day. Look forward to seeing you online and in class.